Hello students, welcome back. Let's go to section 2, solutions of differential equations. Here, we are going to analyze solutions. What do you mean by a solution? A certain expression of t is called a solution if that expression satisfies the given differential equation. You see, if that expression, whatever it is, plug that into y, and then all those derivatives accordingly, and then it satisfies the original equation, then it is called a solution. And most of the time, a solution is valid in a certain interval, and it has to be an open interval because we're dealing with derivatives here. This is differential equation, and if you have a closed interval, at the end point, we can't have any derivatives there, so it has to be an open interval. And that open interval, where the solution is really a solution, is called interval of definition, or there are some other names: interval of existence, interval of validity, domain of solution, and so on and so forth. There are many, depending upon the authors, but our textbook author typically uses interval of definition, so that's the term I'll try to use. Now, sometimes if a solution is written as y of t as something something, an expression of t directly, then we're going to call it explicit solution. But sometimes we may have some implicit expression. Most of the time, implicit expression can be solved with respect to y in a certain interval, but not always. So explicit solution is usually better, but many times they are not available. Okay, most of the time they are available, but many times they are not available. All right, next term. Most of the time, there are infinitely many solutions, you see, because you'll have to take the antiderivative maybe multiple times. Each time you do that, there are integral constants coming out. They are undetermined constants. So we have family of solutions, a family of infinitely many solutions. We call them general solution. So if I have general solution, that means not just one solution, but the chance is there are infinitely many. And you're going to need some more conditions to identify among this family which one is the right one. I hope I made sense, but look at this kind of expression. It's really hard to make any sense out of these until we actually see some example. So let's move on. Here are some examples of explicit solution. You see, y equals to phi of t form, y equals to 1/16 t to the 4th power. Again, I'm not asking you to find this solution out of the given differential equation. No, that's something we're going to start doing from next week. Let's just analyze the solution. So, is this really a solution? Well, what's the derivative? Derivative is 4/16 t to the 3rd power, right? And 4/16, that's nothing more than 1/4. And then t to the 3rd power, but you see, you have t times something, so let's rewrite it like this. Let's put some more space in between. And then this is t times, let's see, 1/4 t squared, that has a matter of fact 1/16 t to the 4th power, total thing to the 1/2 power, which is precisely what we have over here, isn't it? So yes, indeed, this is a solution. We just found out. We proved it. Well, this is just power function, so it is valid everywhere from negative infinity to positive infinity, and the interval of definition is therefore negative infinity to positive infinity. Let's see. Yeah, here's a verification, and by the way, you can use computer algebra system to verify as well. What am I calculating here? Y of t is given as 1/16 t to the 4th power, this very thing. I use Mathematica to define. And I'm calculating this y prime of t minus the right-hand side. T times 1/2 power of y. So if this is correct, left-hand side minus right-hand side should be 0. Indeed. Oh, wait a minute. It's not 0. Oh, yeah, it is 0. T cubed is here, and t times, this one is t squared, t times t squared. So it should be 0. The reason Mathematica sometimes does things like this is because Mathematica is based upon complex numbers. In real number system, square root of t to the 4th power is just t squared, and then we have simplification and everything fits. But if you go to complex number system, and the radicals behave a little bit funky, and therefore Mathematica generates a little bit more general form, but you should be able to see through. How about the next example here? Well, we want to find out x prime, x double prime first, and then plug those in, and let's see, what's x? T, e to the t power, no problem there. What's x prime? Looks like you'll have to use the product rule to figure it out. Good time to review your calculus skill. Derivative of the first function times the second function, plus first function times the derivative of the second function, which is just itself. It's an exponential function. By the way, 1 times something, I don't have to write it. So there goes the derivative function. How about the second derivative function? Derivative of e to the t stays at e to the t. And then derivative of t e to the t, product rule. Wait a minute, we already did it. That's the derivative. Therefore, we can simplify it as 2 e to the t power plus t e to the t power. And we have the original first and second derivative. All I have to do now is to plug those into this and see if we actually get 0. Do we? It's not a difficult computation. I'm going to leave the details to students. Here's verification through Mathematica. X is defined like this, t to the t power, and x double prime minus 2x prime plus x. Simplify. Do we actually get 0? Yes, indeed. How about the next example here? This is a little bit more worthy because unlike the previous example, we have radical here. So this expression is not always valid. When t is greater than 2 in this interval of definition, yes, it makes sense. Also, it'll make sense in negative infinity to 0 as well. You see, between 0 and 2, this expression is negative, so this square root is invalid. Greater than 2, this is positive, so it's okay. Less than 0, that 2 is going to be okay. But this problem asks you about 2 to infinity only, so you don't really have to worry about the other interval of definition. Okay, let's check. How does it work? Let's see, what is y prime? That is, let's see, y is t minus 2 over t, and that's thing to the 1/2 power. So y prime is therefore 1/2, and then the same expression, and subtracting 1 from the power. And then what do we have to do? We have to multiply the derivative of the inside, right? Multiply by the derivative of the inside. And the derivative of the inside looks like we're going to get a quotient rule there. Denominator squared, and then what's the numerator here? U prime v minus uv prime, the derivative of the numerator, which is 1, and then denominator, minus numerator times derivative of the denominator, times 1. And I don't have to write times 1, so let me remove those, and here goes the derivative. Can you simplify? Let's see, t minus t, and then minus minus plus, so this whole thing will become 2. Yeah? And then this 1/2 and 2 will cancel each other out. And looks like this is what I'm going to get. Is everybody happy with this computation? Okay. So, how do we check? We just check the derivatives. So let's put everything to the left-hand side and let's see if we actually have what we want. T squared times y prime. What is that? T squared times, that's y, times, that's y prime. And do we have cancellation? This t squared divided by t squared, okay, that's 1. That's 1/2 power, that's negative 1/2 power. They two will divide each other out, and we're going to get just 1. That's precisely what we wanted all along. So, if you are given a general solution, can you check whether that's a solution of a given differential equation? Can you? You should be able to. If you know how to take derivatives and the algebra could manipulate, you should be able to do that. I left some exercises as homework problems, so please go ahead and do those. I think we went through enough. And let's go over to implicit solutions. Okay, here's a differential equation, and I'm not asking you to solve this differential equation. Here is a solution and analyze it. This is an implicit solution. X squared plus y squared is equal to 1. It's possible to solve for y in most points, but not completely. We have plus or minus square root, and then at the 0 point, we're going to have invalid solutions and so on, things like this. Okay, all right. So let's check. Let's take the derivative. 2x plus 2y dy over dx is equal to, what's the derivative of 1? 0, right? So we begin from here and take the derivative implicitly. Does everybody remember this from Calculus 1? And then let's check. So for dy dx, so 2y dy over dx is equal to negative 2x. And as you can see, 2 and 2 will cancel out. Divide by y. X is equal to y over x. And that's precisely what we wanted. Yes, this is a solution. This is an example of an implicit solution. Here's another implicit solution. Let's see. Haven't we seen this before? This equation. It's familiar. It's right here. So here we want explicit solutions, so time t, so we have y equals to some expression of t. But here, I'm using x. There's subtlety here. X and y are intertwined, and then time t may be something still different. Typically, for implicit solutions, we use xy, xyz, those kind of things, instead of t directly. Many times we do that. Most of the time we do that. So implicit solutions are more related to geometry usually. The explicit, those are time dynamics. Of course, not always, and many times implicit solutions can be solved with respect to one variable given some interval, which is an interval of definition. Anyway, we have 2 over x plus y squared is equal to 1, and let's check if this is indeed a solution. Take the derivative. Oh, by the way, I prefer power form. So let's take the derivative. Negative 2x to the negative second power plus 2y dy dx is equal to 0, right? If you take the derivative of 1. And then we have the denominator here. x squared. So just multiply it out. Multiply by x squared, we get that. And then divide each by 2, then we get that. So flipping one to the other side, we are going to get what we want. Indeed, we got what we wanted. So this is the solution. It's an implicit solution. By the way, what's the relationship between this and that? Well, here, this one is valid all the way because this is implicit. But if you solve for y here, 2 over x plus y squared is equal to 1. So y squared is 1 minus 2 over x. Therefore, y is plus or minus 1 minus 2 over x. Am I doing it right? And compare that with this solution given. This explicit solution is one branch of this, the plus square root, in a specified interval. You see, if we take just a small branch and specify a certain interval, then many times you can go down to explicit solution from implicit solution. But the trade-off is, of course, you're losing some branches and some intervals here and there. You're losing some, but you're gaining more explicitness. There's a trade-off. Is it possible to solve all the time? It is related to the nature of the implicit function, and this significant theorem called implicit function theorem says if the partial derivative with respect to the second variable is non-zero, then it is possible to solve. And here's just a brief visualization here, and here's an implicit solution. Hypothetical implicit solution, x squared plus y squared minus 1 equal to 0, or equivalent to x squared plus y squared is equal to 1. We have a circle here, yeah? And then take the partial derivative with respect to second component. We have 2y. 2y is 0. In that case, it is impossible to solve around that point. Otherwise, it is possible to solve, and here's some visualization. Around the first point, blue point, non-zero, so I can solve. That is this plus square root. Around this red point, non-zero, so I can solve. That's this red. At 1, 0, y equal to 0, so partial derivative is 0 here. So it is impossible to solve around this point, you see. It's impossible to solve. Plus or minus square root meet right here. So you can't solve it and get a nice differentiable function. It's impossible there. Most of the time it's possible, so explicit, implicit, we don't care too much about. Whenever we have solution, we'll call it solution, we're going to move on. That is the theoretical background, why we don't care too much about implicit versus explicit solution. Once you get solution, we're going to move on. All right, we have one more topic to go here, general solutions, but looks like time is running out, so let's talk about 2.6 in the next video along with section 3 materials.